Welcome back to this next video in which we are discussing P groups. Okay, so we've got one final theorem to go, and this one will be called Theorem 5. Okay, so Theorem 5 concerns maximal subgroups of a P group. So remember the definition of a maximal subgroup. A maximal subgroup is one which is maximal with respect to proper subgroups. So we usually denote these capital M. So let's say that M is a maximal subgroup of our P group, capital P. Okay, so there is no larger proper subgroup of P that properly contains M. Okay, so you cannot find me, I will write this out, there does not exist a capital H, let's say, which is still a proper subgroup of capital P, such that M is properly contained in capital H. This cannot exist. There cannot be something that is larger than M and which is still a proper subgroup. Of course, the improper subgroup is still there. That's still a larger subgroup that completely contains M properly. But of course, that's not a proper subgroup anymore. Okay, so there is no larger proper subgroup. It's maximal with respect to proper subgroups. Okay, so Theorem 5 is that if you have a maximal subgroup of a P group, you can always say that the index of the maximal subgroup in the P group, okay, so how many left cosets of M there are in P, is equal to the prime number for which the order of this P group is a power. Okay, so I'll just put that the order of P is equal to little p to the power of some A. Okay, so the index of any maximal subgroup is always going to be a prime if we're working is always going to be the prime if we're working in a P group. Okay, and this is very, very simple to prove, so let me begin by proving this. Okay, so we're going to use Theorem 4 here, that that any proper subgroup is always properly contained within its own normalizer. Okay, and that will apply for our maximal subgroup. So I can instantly say that my maximal subgroup, which is a proper subgroup, will be properly contained within the normalizer of itself in P. Okay, now what does that instantly mean? Well, because the normalizer of M in P is a subgroup of capital P, it must be the case that because this is a maximal subgroup, that the normalizer of M in P is the entire group capital P. Otherwise, if this was a proper subgroup, that would contradict M being a maximal subgroup. Okay, so what this means, of course, then, is that M is a normal subgroup in P. So any maximal subgroup in a P group is instantly going to be a normal subgroup in P. Okay, so it's going to be a maximal subgroup that is normal. Now, don't confuse that with a maximal normal subgroup. A maximal normal subgroup means a normal subgroup that is maximal with respect to proper normal subgroups, but not necessarily maximal with respect to all subgroups. So we describe this as a maximal subgroup that is normal. It's a stronger version of a maximal normal subgroup, much stronger. Okay, now what this means is that we can quotient P out by M. So M being normal means that we can quotient P out by M, and we will get some quotient group here. And what do we know about this quotient group? Well, the thing we know is that it's only going to contain two subgroups. It's only going to contain the trivial subgroup and the improper subgroup, and the reason is that M is a maximal subgroup. Okay, so there are no proper subgroups that properly contain M. Okay, so by the correspondence theorem, there can be no subgroups of this other than the improper subgroup, which corresponds to P, and the trivial subgroup, which corresponds to M. If there was a more interesting subgroup, then that would correspond to some subgroup that was properly in between the two, which cannot exist because M is a maximal subgroup. Okay, and we know that the instant you know that a group only contains two subgroups, then you know what this is going to be isomorphic to. It's going to be isomorphic to a cyclic group on a set of a prime number of elements. Okay, so this is going to be isomorphic to the cyclic group on a set of a prime number of elements. And I suppose we don't initially know that it's going to be the same prime, so I'll put Q. Of course, Q is going to be equal to P. It is going to be the prime P, and in fact I'll just cross this out, this looks silly. So it is going to be isomorphic to the cyclic group on the set of P elements. What else could it be? Okay, because whatever the order of this is, it must be a divisor of the order of the original group capital P, because if you think about what the order of this quotient group is going to be, it's going to be the order of P, which is P to the power of A, divided by the order of the maximal subgroup here. Okay, so this thing is going to end up a power of P. We're saying that it has to have a prime number of elements in. The only prime that is possibly as an option is going to be P. Okay, therefore we can conclude that actually the order of this quotient group is P. Hence what we can conclude is that the index of M in P is equal to P, i.e. that the number of cosets that you're actually going to get when you quotient P out by M is going to equal little p here. Okay, and that's how you can prove Theorem 5. Okay, so thank you for watching this video on p-groups. As I say, the theorems aren't particularly interesting in this video, but they will pave the way for future videos. We will use these theorems in future videos.